flew in directly from Moscow. Clément Fortin, he currently works at the Skoltech. There he has a job as an advisor and a provost. He has an impressive CV with many positions in both academia and also industry. Today, he will talk about the complementary data structure that should enable collaboration on several levels. Please welcome Clément Fortin.
Thank you very much. Thank you very much, David. It's a real pleasure for me to be here. And I hope in this to give you an overview of complementarity and of systems to connect people. And I think it's been the story of my professional life kind of essence. So I will try to show that to you. My early motivation was not AI for AI, because at the time when I started to do research in engineering, and which led to PLM systems, people thought that once you had the product engineering done, that you could automate the manufacturing definition directly based on AI. Okay, and that was research in the early 90s. And so I said, well, forget it. I mean, we need the systems to be people-centric. And therefore, this is the origin of the work that I did. And this is extremely important for, of course, now people don't think, I hope that we will not go back to this type, but I'm going to finish with some ideas about AI and system engineering, right? So that's where I started. Of course, concurrency, like David said this morning, concurrency is extremely important. It's important in terms of errors, and that's what we developed. And I will show you a little later, a system which can integrate product engineering and manufacturing engineering. But this is just to show you. Now, the reason why I'm in Moscow is kind of surprising, right? Because I'm from Canada. I'm from Montreal. I'm a mechanical aerospace engineer. I was professor at École Polytechnique of Montreal for a number of years, and I had the perfect R&D job in aerospace in Canada. But I met this guy, Ed Crawley, who wrote a book in 2016, published a book called System Architecture. He's from MIT, and he's a friend of mine. And one day I went for a conference at MIT, and he said, Clément, I went through my contacts, and he's the founding president of Skoltech, and he said, you're one of the professors who could come to help me to build this new university. And that's why I'm in Moscow in Skoltech. Ed is a great system architecture researcher, and he's done a lot of work, and we went from there. Just to give you a brief overview of Skoltech, very briefly, started in 2011, so very, very recent, in collaboration with MIT, very tight collaboration with MIT. MIT was involved in all phases of development of Skoltech. And now we're in the phase 2, and we have developing now. We still have the partnership with MIT. Initially, it was in all phases, recruitment of faculty, students, all our students went there. And now it's research projects together. And now we're starting a strategic relationship with TUM also. And we have a strong relationship with the University of Calgary in Canada because of petroleum engineering, of course, as you would know. So that's where we are. We started. So Ed Crawley arrived with his, his portable computer with nothing in 2011. But of course, a big project and the support of MIT. This is the campus that we have now that we are installing itself. And the relationship with with Switzerland is that the architects of the building is Herzog de Meuron from Basel, all right? So it's a phenomenal campus. We are now filling the East Ring, 140,000 square meters of space. So it is a very big and very, very nice campus. And it's in the middle of a innovation center called the Skolkovo Innovation Center. And we are the university here, and there are industrial companies. And it's a city because we have primary and high school, apartments, research centers, startup, and so on. So you see that it's a huge initiative, and I have to say that I've been there more than 5 years now. Ed Crowley is back at MIT, but I'm still there. Now, let's get into the topic. You know, when you look at the evolution of systems of the digital enterprise and PLM system in particular, but this is where I'm coming from, it took about 45 years to go from the drawing table to PDM system and PLM systems. 45 years, which is quite some time to go from documents to a digital environment. And MBSE is doing about the same thing, all right, at a much faster pace. Now, the digital twin environment now, in 2018, they're doing all kinds of new things, but then how much time? We have about 5 years instead of 45 to fully integrate PLM systems into MBSE and cyber physical systems and everything. And AI is coming into that space. So we are on a very, very fast transformation cycle in which system engineering is extremely important. Of course now, and I was hearing this morning, and it is, of course, very important. The digital twin is, of course, something critical, but it's easy said and difficult to do because the digital twin, if we're looking at in-service, and I'm talking here about in-service and configuration management in particular, doing the right service for the right version of the product in the field, there are some very, very important roadblocks on the way. Because think about it. Engineering develops a product defined in manufacturing. It's passed to the ERP systems. It's delivered in the market, while the PLM system loses track once it gets into the manufacturing and so on. So you need to close the loop again and trace. And the amount of information that's available is phenomenal. So we can do it on the prototyping level, on the one-to-one, but doing it at large scale with multiple configuration is something that still needs to be done appropriately. This is a picture. I don't want you to read all of this. It's a picture of the PLM environment at Pratt & Whitney Canada, in which I've been quite involved in. And you can see here the product development starts at the top here and goes in the clockwise direction, and the product delivery is here. So obviously, the integration of the multiple bill of materials, the multiple sequence is extremely demanding. And we are definitely in a complex world, in a complex digital environment today. And of course, PLM systems have been able to support some of it, but then why is it so difficult to integrate model-based system engineering with PLM systems? And I will look at it in a more particular angle here. And you know about this, PLM systems are all over. And by the way, you know what's surprising about PLM system? This is where I come from. It's that it's called PLM. It was defined first by IBM in 2000, at the time where PLM system were essentially PDM system, engineering focused. Now they call PLM, but they still have difficulty to manage the whole life cycle. And I think that model-based system engineering is a critical element to get to this full life cycle management capability. So obviously, what we've seen in the last, in the last few years is that we see that we've gone from CAD, CAE, CAM to vertical mockup, and now we're going directly into a model-based system engineering environment. We're leaving the down geometry-based systems to a much more encompassing complexity. Now, if you look at the current structure of PLM system, they're still very much focused on the product structure. They're focused, like David was saying this morning, they're very much focused on artifacts. And this is something that the master model is the representation. And you can, of course, attach a lot of information around there, and it is quite possible, okay? But there are important limitations. And let's see what they are. And of course, we have these, and we can have very complex, and we can fly through. We can do so many nice things with PLM systems today, and they're very, very powerful equipment and software systems, but they're not enough at that stage for model-based system engineering implementation. We need to go next, the next stage. Now, this is the bill of material, data management. This is the core of PLM systems, and we can go from products, assemblies, sub-assemblies, and we could put systems, subsystems. But the limitation is that it's based on artifacts. It's based on components, on physical components. And it's missing some very critical elements, which I'm gonna describe in a minute. And of course, you can put around the master model simulation. You can do simulation right here. Of course, design, tooling, configuration management is extremely important, publication, and you can do all kinds. So around the master model, we used to be able to put everything that was essential for the product management. Oh, thank you very much. Now, I went and said, okay, I've been thinking about this for a while. Why is it so difficult to integrate model-based system engineering with PLM systems? So I went into the data structures. And when you look at the data structure past the master model, which is essentially bill of material, there is an initiative that was done by NIST, National Institute of Standards and Technology in the United States, that defined around 2004, 2005, a new version of the PLM system structure. And it's called the Core Product Model, CPM. And if you look at this, of course, but you can see generally here that the artifact is the core, the features due to artifact, the function is there. So we find a number and behavior is just there. So it's starting to look, of course, it's not as centric, product-centric, component-centric, geometry-centric as it used to be, but it still will make a comparison now with MBSE. All right, so we'll compare the two, and then we'll see what's missing, and maybe we'll get an answer. Why is it hard to integrate PLM with MBSE? Okay, so notice here, artifact in the is definitely part of it, but it's not, when we compare this to MBSE, it's quite different. Of course, you know, system engineering comes from the 60s. It evolved a lot since, and we have the VModel, which is the key element of this, and it's very different from being geometry-centric, right? We are very much on process. If you look at the VModel, right around here, the build or code directly to the manufacturing, and a little bit of simulation now is happening here, so that the design, so it's at the bottom of the VModel is the core of PLM. But it doesn't cover, it's starting to cover requirements and going down now, but it's added to the infrastructure. Now, okay, how do we talk about MBSE? Of course, when we talk about MBSE, we talk about SysML, okay? And of course, MBSE 2.0 will be a phenomenal jump forward, but has to be done correctly. But my reflection here is that let's look at SysML as a model structure for MBSE as a basis. When you look at it, there are three major parts, right? The structure diagram, which is the block definition, interblock package, parametric diagram. That's, okay, looks a little bit like the bill of material. And in the middle, you have the requirement, which is so essential to system engineering, which is so very, very central to system engineering, to model-based system engineering. And then you have the behavior diagram. And under the behavior diagram, you have 4 types of diagram. So that means that behavior is very important. Okay. In fact, if you look at MBSE as such, behavior is key, and it's key at the concept level. And behavior leads to function, which leads to architecture, and so on. All right, so this is key. So obviously, this is very different from there. And what's missing in one, okay, needs to be integrated with this. So the reason why it's hard to integrate PLM with MBSE, it's because some of the elements of MBSE are missing in PLM systems. And particularly states. Okay, we never talk about states. And if you look at one of the newer, I'd say newer, different approach to MBSE, OPM, Object Process Model, done by Dory from Technion at MIT. You have objects, you have processes, you have states, but something that's extremely important, we have relationships, different types of relationships. And this is something that I will come back to earlier. So different types of entities, and here we're not making it overly complex. I'm leaving it to the fundamentals, and different relationships, very, very important. The relationship, you see them quite a bit, very well defined in OPM. They're also part of SysML, and this is something that's very, very important. Let me come back to the original, because this is going to be key. So essentially, if we think about what's happening between engineering and manufacturing, is that we have to go from form fit function. Form is the geometry. Fit has to do with tolerances, assembly, which is so important, and function, which is also extremely important. It comes from the conceptual design. And we have to transfer that into rates, quality, cost, and flexibility. And this is a very important step. So what we did in the initial, what I did in the past there, is that we developed a system which we call manufacturing process management, which allowed to connect real time to the CAD system, to the PDM, and transfer and go to MES and ERP. All right? But what I want to tell you from this, we learned 3 things. Okay? The first one is that if you do the relationship between the engineering bill of material and the manufacturing bill of material, you can structure the manufacturing bill of material to represent time. And therefore, the engineering bill of material represents space. And the manufacturing bill of material is a sequence of steps to make the product. Okay? So the integration of space and time is extremely important. And then that's what we call a complementary data structure. And this is really important. The second item that we discovered, it's the importance of relationships. I already said it, but when we went into, well, the way we developed this is that first it was a university prototype, then we created a company, and then industrialized it with Bombardier Transportation. And now we were playing with, we had to cover 100,000 parts, millions of versions, and so on. You can see the full product development system. And the types of relationships that you have between the system and the product and the manufacturing process is extremely important. Okay? And so that was the second version, the second finding from this. And the third one from a large industrial implementation was that you have to deal with one-to-many and many-to-one relationships. It sounds easy to look at, but this is extremely important, and this is part of complementarity. The one-to-many, you can see many-to-one, all right? You have many parts making one assembly, easy. But when you look at it, if you look at the combustion chamber in the jet engine, the engineering part will be one. The manufacturing part will be many, because you're going to come and weld, you're going to come and add. So the relationship of one in engineering to many in manufacturing, which happens quite often, is essential element of this. And these relationships between the engineering data structure and the manufacturing data structure has to be as evolved and as sophisticated as possible. So not only the entities, so MBSE is much focused on behavior with states, with block diagrams, with sequence and so on. And that's extremely important to represent behavior correctly, with requirements, of course. But you also need sophisticated relationships within the database on each side, on MBSE particularly also. And this is just an example of the relationships between the EBOM, the engineering bill of material, the MBOM on the right, the parts of the material and the features, the process plans, which is the steps which are linked to the MBOM, and the processes themselves, and the resources, which are the machine tools. So what I'm saying here is that in a very, very high level diagram, is that it's extremely important to make sophisticated relationships. And David, the first keynote speaker this morning, absolutely said it for MBSE too. Relationships are critical to do this appropriately. And it's absolutely right. This is what we found. And by the way, the second client of ours was Rolex. Okay, so we went from trains to sophisticated, and Rolex has a very sophisticated manufacturing system. So the CAD PDM to the ERP. But remember what I said earlier, to do the digital twin, we need to bridge fully the CAD PDM under configuration management with the manufacturing system, manufacturing the MES, and the in-service later. And this is a big challenge. And this is what we have, the system product digital mock-up to the design of digital factory. And this is something that obviously needs to run. So this is a complex system of its own on the manufacturing level, where the principles and methods of system design and development apply, and MBSE is critical. Okay, next slide. Now, this is just an example in Airbus Defense and Space, and what I talked to you about is there. The elements that we developed there, it's on the windshield here, but it could be under any system, is the EBOM to MBOM relationships, the manufacturing planning and the supplier management and service management, and also with the in-service or service development also there. So the ideas that we developed on this complementary data structure between engineering and manufacturing, and also the relationships, the different types of relationships, are extremely important to develop a sophisticated model-based system engineering, or model-based engineering, MBE, which is a new acronym that I learned this morning, right? Now, a little few details on the configuration management. Configuration management is an extremely important part of the system engineering and product development, in that let's say we have a component here. Well, I'll just use this one. We have a component here. Whoa. We have a component here. I'm touching the wrong button. And you have engineering and you have development. This is further work that we did, development and testing. You have to realize now that engineering develops the product and it keeps improving. And then at one point, you'll test part of it. When you go in the testing, you will test a particular version which is going to change after. So engineering will evolve differently than manufacturing. So if you look here, this is development and testing. This manufacturing, assembly, and so on will keep moving, evolving on its own, because this is going to, while engineering will keep, and at the end, you're going to have to re-synchronize. And this is key again for the digital twin principles. So issues, there are several bill of material exist for a given product. Okay, we have the engineering bill of material, the manufacturing, and others. But these should be realized into a single BOM when possible to ease the complexity of business. But this is not possible. In practice, multiple bill of materials and multiple versions of the product needs to exist. So it's impossible, because we have a strategy here. Or we make things all into one single master model, or we make into a much diversified, flexible environment. And I think MBSE will need to work from a flexible, diversified product structure and system structure. Very briefly here, if we look at integration, and this is something we said this morning also, and I heard it many times today, is that to do MBSE, you need to integrate under different dimensions. One, engineering to production. One is suppliers to client, and the other one is concept to product, which is the real technical part. And if you need to look at these three dimensions for a successful model-based system engineering implementation. All right? Now, a few comments here on the importance of people. There's only one way to look forward as I get closer to the importance of AI today. People, systems, and machines are making the whole complex system work. There's no way we need people-centric systems. And I'm coming back to your two pillars, right? And you're absolutely right. This is from the NASA's System Engineering Handbook. I could have taken anything. There's two parts of it. There's a system engineering on the left, and there is the project management on the right, the more cost schedule. And these two elements need to be taken care of in any complex system development. And this is extremely important. And I'm very glad to see that in MBSE. And that's why I call that project leadership here. Whoop, what's happening? Okay. Now, about people. The World Economic Forum in Davos in 2016, but they do it regularly, established the 10 skills required for the fourth industrial revolution. To me, I make this as the skills required for a top system engineer, because the system engineer will be the one integrating the systems, and the leadership, technical leadership, is extremely important. In 2020, they've established that the top skills is the complex problem solving, directly related to system engineering. We do system engineering to solve complex and to develop complex systems. Critical thinking, very important. Creativity, people management, coordinating with others, emotional intelligence, judgment and decision, service orientation, negotiation, and cognitive flexibility. You see how much people skills are important here. Of all those, of course, system engineering is there. Critical thinking is how you think. Creativity is how you develop new ideas. And then look at people to people. People management, coordinating with others, emotional intelligence, judgment and decision making, and service orientation and negotiation are all related to people, okay? And the system engineer, to be successful, will have to have for the future these skills taught. All right. So I think that this is where we're going. Of course, we can talk about the technical content of what should be in MBSE, but for the future of leaders in these complex system, in complexity, model-based system engineering, these skills are very, very critical. AI and MBSE. We have one of our top researchers at Skoltech called Evgeny Bernayev, and I organized the PLM conference in Moscow in July. And I invited him for a keynote, and one of the things that he said is this, and I totally agree with him. That's why I decided to include it for you. Models from first principles coupled with machine learning will lead to efficient PLM systems and model-based system engineering. AI will work well if we have excellent simulation-based but cohesive, coherent models of all scales, from 1D to 3D to 4D models. But these are the only way that we're going to have AI and PLM system work well. That means to me that the better our models within MBSE, the better the models are, the better AI will work and support system engineering development for a sustainable future. They're not independent. They're not independent. One thing that I've learned from top researchers in the field of AI is that even for so many sophisticated users, AI is still a black box. Even for the top researchers in the field, they don't know exactly why it works, but it works. To me, I'm a mechanical engineer. To me, okay, Watts developed the first steam engine without knowing thermodynamics. I agree. But then to develop the jet engine and the internal combustion engine, you need some rules of thermodynamics. So we are at the critical time today in digital environments where we have a phenomenal tool that we don't know exactly how it works. And to me, that means to us that we need to be very careful. If you look at some of the recent studies, they say that 43% of the successful companies having a process in place for augmenting and overriding questionable results from AI compared to 28% from those who have not tried it yet. What I want to tell, because in complex systems, AI will definitely be part of it. And for people that have been successful, they say, check it. And to me, that means that we have to put more emphasis on the right-hand side of the V. I say that again. We need to put more emphasis on validation and verification, because we don't know that box. So we need to find the right test case and test deeply to make sure the system will work correctly. On the importance of verification and validation, another part of it, for example, we would be seeing more widespread use of driverless cars if government oversight and automaker level governance capabilities were able to keep up with the technology itself. Okay, we need rules. We need proper rules. We need the government laws. The laws have to evolve. But I'm telling you here as system engineers is that please be very deep in your verification and validation of systems. And we can mention the 737 MAX as an example, but this is just one example. So, and people, this is the chief data scientist from Accenture. We believe AI will transform the relationship between people and technology. And for me, one important message that I want to leave with you from my own experience, in that systems have to be people-centric. They don't go around people. It will not work. There has to be maintained by people, defined by people, and used by people. And even though they make our life easier and we can do better things, it's still extremely important to have that relationship. And one of my last slides is that a reflection which I took from Fluor is that if you look at the evolution of AI and design, and here I make a parallel between design and systems engineering. They're the same to me. All right? So in 1956, design started to exist. And the AI becomes a field in 56 too, okay? And then the sciences of artificial in 69. First mention of design thinking was published in 69. So next year, you have some authors on design thinking, extremely important. And to me, MBSE, system engineering, design thinking, product development, it's all the same. And we'll need to integrate those as quickly as possible, including PLM systems and MBSE. And early adoption came industry 1990s. And in 91, IDEO. How many of you know about, raise your hand, those who know IDEO, right? So IDEO is a very famous design organization in the Silicon Valley. They've marked the design thinking, okay, in 91. And 2001, AI explodes into the industry, and design thinking is spreading from 2000, and now we're at the edge of this, but the maturity of this will not happen until MBSE matures itself. And it's not through SysML. I totally agree with the first keynote speaker this morning. SysML as a language is too complex for engineers in general to understand, okay? So we need a better, simpler, more powerful representation, which have more capability for model-based representation. And one comment here, in the early 90s, we did the contract with Pratt & Whitney Canada. At the time, there was an AI platform based on Lisp that was being tried in engineering, all right, for designing components and so on. And we got a contract to say, can that be applied in manufacturing? We did the study in depth, and we found that it was not possible. And you know the reason why? It's because the relationships at that time in this type of application, which was list-based, were not sophisticated enough to represent the manufacturing reality. So this is something that you need to, again, I'm stressing the importance of relationships, the types of links that we make between components as being extremely important. Whoop. Why am I getting this? Let's see. Okay. And my last slide, verification and validation are becoming much more important in sophisticated model-based system engineering, and particularly when AI becomes a player in our systems. Thank you very much for your attention.
We have time for questions. Are there questions concerning Clément's excellent talk?
You talked a lot about relationships, very commendable. But have you found a way of modeling implicit relationships? You mentioned the example of manufacturing like a block of metal. And you will affect one tolerance, which is on that CAD design. But say if you have a deviation request that's accepted because you say we can still live with that, obviously you have to see all the other parts that are affected by that tolerance. Is there a way in your modeling that can solve
Well,
that?
I think that if you're going to do model-based system engineering, you have to make those explicit. That was exactly the problem when when people thought that if you have the product defined, you press a button and manufacturing comes, right? Because manufacturing has a lot more implicit information, and that's why human-centric applications are becoming more important. So what I think the way to do this will be to define new relationships based on to represent the implicit form.
But the implicit relationship comes from a tree, if you like, or a path of relationships that somehow is linked somewhere. If you put in an explicit one, then you create a constraint on your model, which might create big problems when it comes to variant
Well, that's what I see, is that what we found in practice when we did the industrial implementation, it's the kind of relationships and the types of relationships, and I don't go into the details because this is in the know-how of the application, become extremely important. You're right, absolutely. So if it's a relationship that over constrains, you're going to be in trouble. Yes, for sure. And that was the thing that we found initially on that Lisp application, is that it rendered the model very, very heavy and not usable.
You're emphasizing the importance of verification validation. To some extent, I agree, and some not. The key element is, let's say, as you just look to that picture you have on the wall, it happens very late. If you find the problems late, we run in deep trouble in terms of the time and cost budget we have. So the key is we have to bring V&V more to the forward part.
Yes.
And in that sense, topic of today, digital twin simulations may help.
Yes.
But I think it's really important not to have it in the rear part, so in the right leg of the VModel, but really think deeply how you can test and solve problems early on.
Yeah, of course I agree with you. You cannot leave it late. And for me, the VModel is a evolution. It's a spiral, right? You need to check as quickly as possible. That's why I believe in agile system engineering, where you do small developments, check, test, small development, and move around in a spiral. And probably you have to move with a very tight initially, like was mentioned, and then you open it as your product evolves. But you cannot wait late to check and do that. You're right. This is one of the weaknesses of the VModel, of the system engineering. I think system engineering must be improved. It's not, to me, it's too, it would seem to me to be too risk avert.
I think the problem is not of the VModel, it's of reality that if you want to perform system tests, you need the system typically.
Yes.
And these you have late in the development. So
yes.
The key is really, and
the virtual
digital stuff may help us bring it forward.
Of course. Yes. And you need to take care of configuration management at that step too, because your engineering will keep moving and you're going to be doing vertical testing. Vertical or physical, you still have the same problem to solve, right? Absolutely. Yes.
More of an open question. MBSE, PLM. PLM has all the power today. Where do you think we'll go? Will PLM move to MBSE? It's going to be tough. Or where is the MBSE power to bridge to PLM?
Well, you
where
saw
is
it
going?
You saw it in the presentation of Siemens today, right? PLM will have to embrace the concepts of MBSE. They already did it to a certain extent because some of them integrated with Cameo, some of them have their own, SysML integration, because MBSE, I would say, it's way too limited, is linked to SysML. We have to raise the level of model-based system engineering 2 and then bridge PLM and MBSE. So, of course, the critical mass is in PLM in terms of business and so on, and the expertise is there, but we need to go away from the artifact-centric, bomb-centric data structures. And one of the greatest difficulty, and when we developed the manufacturing process management, and I had many discussions at the time with the people from Unigraphics, okay, before Team Center. And the problem is legacy. It's not going to be easy. Not going to be easy. So maybe there'll be newcomers coming that will have a different approach, but the merge is definite coming. No doubt about it. Okay.
Is there an additional question?
Thank you. I did not get really the point why to get away from the artifact model. Is it not rather the point to broaden the scope of an artifact so it can also include some, and then you can stick to the old PLM system, and in fact your model-based system is then simply a new BOM or a bill of artifacts or broadened artifacts.
Sure, sure. I agree with you that it's a, what I mean there is not going, of course the artifact is a physical, it's the simulation is attached to it. It's a very important, but we cannot just be artifact or BOM focus. States are important. Behavior is so important that it's gonna have to be part of new PLM system approaches. That's what I think. But you're right. Thank you very much for your comment.
I love the part that you meant, the AI part of the presentation, and I saw nobody ask, so I said I have to ask because it's part of my hobby things and I love to do. Question is, from your base of your experience, how long do you think it will take that the system engineering community will start do things and verify these AI implementations? Because they're a little bit, let's say it's a little bit, based on my experience, painful, because software engineers did ask these questions 30 years ago. Do you have, I mean, like a prognosis how long it will take?
If we don't want huge catastrophic failures like the 737 MAX, the time is now. And that's why I wanted to talk about it, because I think this is so important today.
So learning by pain.
Of course, and we've always done it, but hopefully we'll be smart enough to do it right, better. Okay? Thank you. That's it. Thank you. Thank you.
Okay, in this case, we continue with